Good afternoon, everyone. Okay, so I am Priyank Vasu, and I'd like to thank the organizer for giving me the opportunity to present our work here. So I'm going to present the time-like minimal surface in Laurent-Minkowski 3 space with arbitrary ends, which is the joint work with Subham Paul and Dr. Rahul Kumar Singh. Okay, so as previous speakers have talked about the minimal surface in R3 and maximal surface, which are the space-like surface in Laurent 3 space, which has the induced metric is Riemannian. Now we will talk about when induced metric is Lorentzian on those surface, and plus the condition they are the zero mean curvature surface. Okay, so the definition locally they will look like from like U is the open set from R2, then we take a map to Laurent 3 space, which is denoted by even 3, and if this is the conformality condition and each coordinate satisfy the wave equation, then that map is the time-like minimal surface. So as previously we have seen, like space-like maximal surface, space-like zero mean curvature surface, which are called maximal and minimal surface, their study has been done with the complex plane. Okay, complex play a crucial role there, but in the surface, time-like minimal surface, that role is shifted to the split complex number. And what is the split complex number? They have many names like hyperbolic number, paracomplex number, and different names. So split complex number is number z hat, which is x plus ky. K is imaginary unit, which is k square equal to 0. Okay, so the norm here is the norm of z hat is x square minus y square. Okay, and the function is defined in a split complex plane is uxy, which is real part, and k vxy, which is imaginary part, and we say they will be split holomorphic if they satisfy CR equation. So it is like this CR equation is not usual CR equation, which is in complex. It has like there is no negative sign, so we can see there are difference between complex and split complex number, and the difference which will play a major role in defining the time-like minimal surface with arbitrary ends is the pole of the split complex number. So a split complex function, like we can see, is 1 by z, that can be written as this, and we can see it is not defined on the line, which is, if this is our split complex plane, that is x equal to y, and that x equal to minus y. So now in the complex plane, whenever we are talking about the pole, we are talking about the single removable point. But in split complex, that becomes the whole cross section, the whole light-like lane. Okay. So moving forward, we can define the split meromorphic function, which is the reciprocal of split analytic function. And if f has 0 at p hat, then we will say then g has the pole at p hat. Okay, now keep in mind whenever the hat appearing, I will be focusing on split complex. Now there is a Weierstrass type representation, which we have seen for minimal surface and maximal surface itself. But in terms of split complex number, so let omega hat is an open subset in D, which is a split complex plane. G is a split meromorphic function. F is a split holomorphic function on omega hat. Then first, fg square is a split holomorphic. That means the order of poles of G should be, and order of 0 of F should be like order of F, zeros of F should be twice F, order of poles of G. And imaginary G should not be identically 0. That means first that surface is well defined. And the third condition, which is called the very important condition to define that integration real part of it, that for any loop gamma hat defined in a omega hat, that triplet integration should be 0. Okay, then this G hat and F hat called the Weierstrass data for X hat, our minimal surface. Now, the third condition there, that integration around any closed loop gamma hat should be 0, that condition called the period condition. Now, and induced metric from even 3, Lorentz 3 plane, that metric is conformal. We notice that, and that matrix conformal factor look like this, and its time-like minimal surface also have degenerate set of singularity, which will be denoted by this set. And also, because E13 is nothing but is Euclidean space E3, so we can also put the metric from which is coming from E3. So that metric will be represented by H hat E3. And we say a time-like minimal surface is E3 complete or weak complete if it is complete with respect to the matrix which is induced from E3. Okay, so now we are ready to define the pole of time-like minimal surface, which is like omega hat is our open domain. Still, G hat is our split meromorphic function, F hat is our split holomorphic function. Then we can define this triplet in E13. It is split meromorphic function each coordinate. If any of this coordinate has a pole at P hat, we will say that whole cross section of this will be the our end of that time-like minimal surface. Then we will integrate it and we can find our time-like minimal surface. Okay, and we will say that end is weak complete if we found a neighborhood around that end, and that is complete with the metric induced from E3. Now, the difficulty to define such a time-like minimal surface is that because now the domain itself having ends is become disconnected. Each disconnected component is connected, so whenever we are defining the closed loop there, that portion itself is well defined, but and here the surface is well defined, but there is no relation between these two, it seems like. So whenever such a, so defining the period condition here and solving it becomes a little bit more difficult. So how we try to solve it, they are not related here, but this kind of problem, sometime we move in higher dimension and try to see if they are related in higher dimensions. So we will try to solve it in higher dimensions. Okay, so how we are going in higher dimensions? For that, I am defining the bicomplex number. Bicomplex number is defined by BC, that is a ring, and the topology on bicomplex number is in R4, and that is x1, x2, x3, and x4, where I is imaginary unit, j is imaginary, and k is imaginary. And I, j, and are different imaginary, where I square and j square equal to -1, and k square equal to 1. Okay, so they are different than quaternions, but and here the name Y bicomplex is appearing, the second representation can be seen. Okay, so now we can see in the bicomplex number, split complex number as the first coordinate and the fourth coordinate, it's k appearing. So split complex number is already sitting in the bicomplex. Now, the zero divisors of bicomplex and split complex are defined in this way. Okay, so now there is one more representation which is much more helpful to do the analysis in bicomplex numbers, and that representation is called the idempotent representation. In that, what we do, we define two split complex number, which is E and E dagger, and we define any bicomplex number Z tilde. Here is B1E plus B2E dagger, where B1 denoted by this and B2 denoted like this, and beta 1 and beta 2 are in CI. Why I'm writing in CI? Because here that is the complex plane where imaginary unit is I. And then we can see even in the idempotent representation, we can represent D as this, the real part of beta 1 and E plus real part of beta 2 E dagger. Now, there are many ways to define the conjugate in bicomplex number, but the one we will be using is defined as the star conjugate, which is nothing but the beta 1 conjugate. Beta 1 is complex, beta 2 is again complex, then their respectively complex conjugate. Then we will define it is a star conjugate of Z tilde. And again, little bit note, whenever tilde is appearing, that means that function or that element is in bicomplex. Yeah. So now we are ready to define the functions in bicomplex number or bicomplex plane. That is, a function is also, we will defining in the idempotent representation, a function f tilde can be written as the g1e plus g2e dagger, where g1 is function of beta 1, beta 2, and g2 is again function of beta 1 and beta 2 in general. But there is a beautiful theorem which is defining the holomorphic function in bicomplex, which says f tilde in bicomplex is holomorphic if and only if g1 is first of all only function of beta 1 and g2 is function of beta 2, and they are respectively holomorphic in their complex plane. Same goes for the meromorphic function, and this says that they should be defining like g1 should be function of beta 1 only, and g2 is function of beta 2 only, and they should be meromorphic respectively. Now, defining poles, f tilde has pole at p tilde, which is bicomplex, and p1e plus p2e dagger if g1 has the pole at p1 and g2 has the pole at p2. And now this is one important result I can say that will say if this star conjugation is satisfied, this equation 0.5 is satisfied, that means that function f tilde restricted to the split complex, which is lying inside the bicomplex plane, then its image will also be the resultant split complex plane. So now the restrictions become split complex valued function if f tilde satisfies this equation. So I will be in further presentation, I will be referring it this equation by 0.5. Okay. So now with keeping this mind, there is one result which says that the f tilde is holomorphic, then its restriction is split holomorphic. And if f tilde is bicomplex meromorphic, then its restriction in D is split meromorphic. And now equation 0.5, because G1 and G2 here, they are the complex function. So equation 0.5 also can be turned into some condition on G1 and G2, which is if G1 is conjugate symmetric and G2 is also conjugate symmetric, then we say the H tilde, the function in complex bicomplex number, will be satisfying equation 0.5. Now we are ready to define the bicomplex extension of zero mean curvature surfaces, and this is defined by this integration, like phi tilde is defined by the integration of g1 minus g like this. We are familiar with this representation because it's a pair in the Weierstrass-Enneper representation for Timelike. Okay, so every bicomplex extension of zero mean curvature surface can be look like this, where f is bicomplex holomorphic and g is bicomplex meromorphic. Now, for the not using this long of sentence, I am calling them bicomplex surface. Yeah. So we are ready to define the period condition or period problem in bicomplex surface. So any loop gamma tilde, which is defined in the bicomplex plane, if the real part of this integration satisfy and it is equal to 0, then and where we have already removed the pole of bicomplex number p tilde, then we say this is the period condition for bicomplex surfaces. Now we know if equation 0.5 is satisfied, then this restriction of it will give us the Timelike minimal surface, and the restriction of g tilde and restriction of f tilde will give us the Weierstrass data of our Timelike minimal map. Okay, so now only thing is remain to solve how we will try to solve the period problem in bicomplex. So solving the period problem in bicomplex, we will use the maximal period problem for maximal surface, which is defined like this. Now we have seen it many times till now, like omega is open set in Ci and G is complex meromorphic, F is again holomorphic, satisfies these three conditions. Again, the third condition here is period condition for maximal surface, and G and F are called the Weierstrass data of our resultant maximal surface. Yeah. So, yeah, and one thing to notice here, this is not the usual notation which my previous talks people have talked about, because you have seen it is reparameterization on that. And why we have reparameterized it? Because we have to extend it and it should match with our bicomplex. Okay, so this reparameterization is losing some condition, like before this, when G was here, it was related to the Gauss map of maximal surface, but here it is not related to that. So now we are ready to tackle the period problem in bicomplex number. So first, what we'll do, we are taking the two maximal surface, say x1 and x2. Here I am representing it with K, and their Weierstrass data, G1 and G1F1 and G2F2, and they satisfy the period condition in complex plane. And we are defining our G tilde, which is the bicomplex function, which is dependent on the Weierstrass data coming from our maximal surface. Say G tilde is defined by G1 E plus G2 E dagger, where G1 is coming from first maximal surface and G2 is coming from second, and similarly we can define the F tilde bicomplex surface in this way. So we know if G1 and G2 are meromorphic, then G tilde is bicomplex meromorphic. Similarly, F tilde will be bicomplex holomorphic. Now, the real period condition which we have defined, the bicomplex number, is beautifully converted into the period problem in first maximal map. This is the maximal map here. This is the second maximal map here. So if we know the solution of a period problem in maximal surfaces, then we can solve the period problem for bicomplex map. Yeah, and furthermore, if we know this real period condition, if it's satisfied, then real of phi is defined, well defined, even if whole phi tilde is not defined. And the restriction of this will give us the time-like minimal map. Okay, and if we put the conjugate symmetric condition, that was the condition with equation 0.5, that means the restricted map will be from split complex plane to split complex plane. Then we reach to our first result, which says that if x1, x2 are two maximal map with Weierstrass data G1F1 and G2F2, then we can define our bicomplex surface, bicomplex meromorphic map and bicomplex holomorphic map in such a way which satisfy equation 0.5, then its restriction defined in this way will give us the time-like minimal surface, and the Weierstrass data will be the restriction of G tilde and F tilde. This is one example. So example says that if we are defining our Weierstrass data in such a way, then this is our first maximal surface, this is our second maximal surface, and we have chosen in such a way so they also satisfy equation 0.5, then this is our defined time-like minimal surface. Now, based on this construction, we are now ready to study the ends of time-like minimal surface. So first, what we are doing, we are trying to see the asymptotic behavior of simple ends. So what are the simple ends of time-like minimal map? If a time-like minimal surface is defined in this way, then we say x hat has simple poles. If x1 has a simple pole at p1 and x2 has a simple pole at p2, and this p1e plus p2e dagger will be sitting in the split complex domain. Now, we know if we know the asymptotic behavior of maximal map x1 and asymptotic behavior of maximal map of x2, then we can move forward to see the asymptotic behavior of our time-like map. And this study has been done with like Imizumi in his work. But what we have done, we have put the symmetric conjugate because we need the restriction to be from split complex to split complex. So keeping that change in mind, we have proved the theorem from Imizumi work in this way. So the maximal map with conjugate symmetric Vistage data have simple ends asymptotic behavior look like this. Now the thing only we need to worried about, because this asymptotic behavior are in polar coordinate, but still we haven't seen the polar coordinate of bicomplex number and how the restriction of that polar coordinate will behave in the split complex number. So beta 1, beta 2 are in Ci, then beta 1 can be written in the polar coordinate in this way, where R1 is the radius, and beta 2 can be written in this way. Then we have seen like the restriction, this bicomplex number restriction, Z tilde, in D will be only when theta 1 is either 0 or pi, and theta 2 is either 0 or pi. Then this is the restriction in polar coordinates in split complex number look like, where epsilon k is plus and minus 1. And it makes sense when R1 is going to 0, then we will be approaching this line from this side. And when R2 is going to 0, we will be approaching this line from both sides. Plus and minus 1 will be representing that. So this is the theorem we reach, like time-like minimal surface with simple ends. And these are the 4 types of simple ends it can have. Now, as per the title of this talk suggests, we are ready to define the arbitrary number of weak complete end. First, so the construction we will follow step by step. So we need G, K, G1, G2, conjugate symmetric meromorphic map, which has poles at Pi of order Xi. Done. Then we need our maximal surface, which is x1, x2. They should satisfy the period condition. So satisfying the period condition, that Vistage data will look little bit big, but it is coming because we need n ends, and we will make them in weak complete. So it will look like this, and Pi and AK, BK all will be real, because we need one more condition on our Vistage data for maximal surface, that will be the conjugate symmetry. Then we are ready to define G tilde and F tilde in such a way where, and it will be satisfying equation 0.5, because our GK and FK are conjugate symmetric. Now, because G1 and G2 are meromorphic, and they have pole at Xi, but their pole should be the same order. If they have the different order pole, then the pole in the bicomplex number, that will behave little bit radically. So what we will do, we will try to make, because we are choosing that Vistage data, we will make those pole are equal. That is here. That means now we can ensure the restriction has pole of order Xi. Then problem is solved. Now with this Vistage data, when we will restrict it, we will get the time-like minimal map, and the Vistage data will be G tilde restricted on D and F tilde restricted on D, and it will be defined on whole over split complex plane minus these punchers plus their zero divisors. And we reach the result, which says that we show that the previous defined Vistage data will give the existence of time-like minimal surface with arbitrary weak complete ends. Thank you.
Questions? Priyank, the last bit was a bit fast for me.
Yes, ma'am.
Yeah, so last bit, can you say a little bit like, yeah, from here.
Yeah.
F1, F2, yeah.
Yeah. So what is happening, ma'am? Construction shows that if we have two maximal maps,
right,
where Vistage data is conjugate symmetric, then we can define the bicomplex extension to that, which is G tilde, G1, G2, E dagger, and F tilde, which is F1, F2, F1E plus F2 E dagger. and where G1, F1 and G2, F2 are vistas data for maximal surface plus additional condition, they are the conjugate symmetric. Then the restriction of G tilde and restriction of F tilde will be giving us the vistas data for time-like minimal map.
Okay. Very nice. And then after that?
Yeah, this is enough to show the existence.
Existence. Okay.
Yeah, we have given the vistas data for arbitrary number of n.
Okay, yeah. Great, thank you.
Thank you.
Okay, if there are no more questions, let's thanks the speaker again.